Today we will talk about electrical and electronic components as dynamical systems or parts thereof. Electrical components are an integral part of dynamical systems, and they are essential to the proper behavior of just about any machinery, including in aerospace, automotive, and other mechanical systems, as well as those operating, say, in the surgery room or in the radiation treatment room. So the components that we will talk about include resistors, denoted by a rectangle, capacitors that are represented by two plates parallel to each other, inductances represented by a solenoid. Okay, they are also called solenoid. We will also talk about electric motors, which on the one hand take as an input a certain voltage and a certain intensity, and at the other side give you a certain angular speed and a certain torque. Electric motors are essential components for understanding the link that exists between electrical systems on the one hand and mechanical systems on the other hand. We will also talk about power supplies, that, if you may remember, can be voltage sources or current sources. So let us begin and describe how these components work. For that, we will begin with resistors. Why? Because they are the simplest items. When I talk about the resistor and any other component, I will assume that I have a line so I said a line and the ground. The ground will be modeled as this. The line will be above it, and we'll be talking about the voltage V that separates the potential of the line from the potential of the ground, and we'll be talking about the intensity as the voltage the current that goes through the line. A resistor can be seen as a choke point where the current is bounded by what it can go through. And if the input voltage and the input current are given, we can conclude what the output current and the output voltage should be. Notice that the current may flow forward or backwards. So all the quantities I'm going to talk about are algebraic quantities. That is, they can be positive or negative, or zero, of course. A resistance R is such that the following relationship holds. If V1 is the voltage at the beginning and V2 is the voltage at the outset, okay, we have I1 is equal to I2 and V1 is equal to V2 plus R times I, where I is I1 and I2. Okay, so we can write this in matrix form, and we get that V2 I2 will be equal to so V1, sorry, so it's going to be a 1 if I represent that as a matrix, minus R 0 1 times V1 I1. And so what you see is that we use V and I are sort of the core variables through which we describe the behavior of the resistor. This will remain true for other elements as well. So the resistor is the simplest element, and it is very useful. What you may notice is that V2 I2 as a function of V1 I1 is a linear function. And so, through that mechanism, will actually prove to be quite useful, because what we have seen previously is that the Laplace transform is most useful for linear differential equations. Okay, and by the way, talking about Laplace transform, you get that V2 I2 hat is just likewise equal to 1 minus R 0 1 times V1 I1. Okay, now let's look at some other components. And so the other components include the capacitor. A capacitor satisfies the following. Okay, you have I as the input intensity, I1, I2 as the output intensity, and then likewise we have V1 and V2 as the voltages at the input and the output of the system. Okay. Then we have that the voltage across the armature, okay, so that voltage V is going to be satisfied dV dt is equal to, is going to be proportional to the intensity entering the capacitor, okay? And we will have that the input and output currents are going to be once again the same. I1 is equal to I2 is equal to I. Now, why is that? It is because when the current comes into the plate here, it charges those plates, the left plate, with electrons negatively. And these form these yield the creation of positive charges on the other side with the corresponding electrons flowing out. Okay? So now, so there is a notion of capacity. Okay? And the notion of capacity is such that the larger the capacity, the more you can store electrons into the capacitor. Okay? So, what that means is that the voltage across the armature should go slowly as a function of the intensity. And so, what we get is that C times dV dt, okay, is equal to I1. Okay? So the more C, or in other terms, dV dt is equal to I1 over C. So for a large capacity, the voltage grows slowly, and as a result, the voltage across the armature grows slowly, and you can store a lot of current until the capacitor reaches maximum charge, which is when there is the creation of a lightning across the two armatures of the capacitor. Okay, so what we get is that V1 is equal to V2 plus dV dt plus V. Okay, and dV dt is equal to I1 over C, which is I over C. And what we get, the final one, is that, well, that's all we get, really. Okay? So we can write this as the equations that drive a capacitor. Again, V1 and V2, yes, V1 and V2 are again linear functions of what's unknown. Okay? The relationships here are linear, although there is a differential equation. Okay, so we will now look at another element, which is so we will look at another element that is the inductor, okay, on inductance. So an inductance works as follows. It looks like a solenoid because it is a solenoid, okay, which is wrapped around usually a piece of metal, okay, soft iron. The ground is here, V1 is here, V2 is here, and I is here, okay. Again, I1 is equal to I2, okay, so no particular big deal here. And what we get is that the voltage here, okay, V, the voltage V is equal to L di dt, where I is just I1 and I2, okay. So this is another kind of a differential equation that leads us to V2 is equal to V1 minus L di dt as, again, a set of linear equations in intensities and voltages across the solenoid or the inductance. Now, let's look at another item. First of all, before we go into anything else, let us talk about typical circuitry. So RLC circuits. These are standard circuits, and they are the equivalent of the mass spring system. So they are the mass spring system of electrical engineering. What are they made of? Well, they are made of an inductance, a resistor, and a capacitance. And we literally close the loop. Okay? Something like this. So the intensity here that flows is the same throughout. And what we have is that the voltage across this guy, we call it V1, V2, and V3. The way we have arranged things, V1 plus V2 plus V3 must be equal to 0 because they sum up to the same, okay? You take V1, V2, V3, you climb, and then boom, okay? So, let us derive the equations of the RLC circuit, okay? Where we have R here, L, and C. We write L di dt is equal to V3. R times I is equal to V2. And then C times I is equal to dV1 dt. Okay? So with all these, okay, we can first use the Laplace transform. The Laplace transform reads as, for LDI, for this equation, it will read as L times S times I hat minus I of 0 is equal to V3. This one will read C times I is equal to S times V1 hat minus V1 of 0. Okay, so let me recall the color codes. The third one is simply Ri is equal to V2. Based on these, we get the following, that this following equation is for V1, V1 of 0 plus C times I divided by S my mistake. In the previous equation, it was not C times I is equal to V, okay? It is, I made a mistake here, sorry, it's not a C here. It goes here, okay? So with that correction, we get that the C doesn't go there, but instead goes here. So it's going to become C times SV1 minus C times V1 of 0. So if I recap and correct this, I obtain that V1 hat is equal to V1 of 0 divided by S plus I over CS with a hat on top of the I. V3 is already given, okay? We have V3 hat is equal to L times Si minus I of 0 with a hat on top of the I in such a way that the complete equation of motion, or the equivalent equation of motion for a RLC circuit will be, let me make a little bit of room here on top, something along the lines of, so V10 over S plus I hat over CS plus V2, which is R times I hat, plus V3, which is L times SI minus I of 0, is equal to 0. Now, we recognize the familiar components of a second-order differential equation. Indeed, suppose that I multiply this equation by S, I obtain V1 of 0 plus I hat over C plus RS I hat plus L times S squared I minus I of 0 is equal to 0, or in other terms, I over C plus RSI plus L S squared I is equal to V1 of 0 plus, minus V1 of 0. Hold on a second here. Yes, okay, this is correct. Minus V1 of 0 plus L times I of 0. This is a standard equation for second order system in the Laplace domain. Okay? Now I let you think about what happens if, for example, there is no resistor in the circuit. Okay? You should be able to find that this corresponds to sustained oscillation. Okay? Alright, so this is our first electrical dynamical system, and it is a dynamical system which is, as I said, the mass spring system of electrical engineering. Okay? It has the same equations as that of a mass spring system. Now, let us move on and observe other things that are very important for our electrical systems. One of them is what happens when you do the junction of several systems. Okay? So, for example, let's assume that we have one line, another line, and they merge. Okay? Then the voltage across the first line, the voltage across the second line, and the resulting voltage V must all be equals. The current I1, the current I2, and the current I3 satisfies I3 is equal to I1 plus I2. Again, for a junction like this, the voltages and intensities of the different elements that are joined together are related by a linear set of relations. Clearly, simple linear set of relations. Another thing is, so we will see other elements involved in the future, okay, that yield, instead of current additions, voltage additions, okay. So, for example, if we take two pieces of wire and we mount them like this in parallel, okay, sorry, in series, and there is some equipment here and some equipment there, such that the voltage across this one is V1 and the voltage across this one is V2, okay, then the voltage across both of them will be V1 plus V2. Alright, and by the way, I1 is equal to I2 is equal to I. The same intensity everywhere. Now that we have briefly seen interconnections, I want to talk about other elements that are super useful. We are now going to talk about the operational amplifier. The operational amplifier is represented as a triangle with inputs with an armature and an output. If the input is V, if the output is a very large number, K times V, okay, where K in absolute value is much bigger than 1. The operational amplifier is therefore indeed an amplifier, first and foremost. It is used in a wide variety of contexts. However, the standard way we are going to use it in this class is by drawing the following diagram. Let me erase V here and make it more visible by putting some colors. So, as I said, the standard way is connecting the plus pole here to the ground. The minus pole here will be connected to an input voltage V1 and input identity I1 using a particular electronic component still unspecified. Now, notice that no input, no current goes into the amplifier nor leaves the amplifier. But on the other hand, what we do is we divert this current and we pass it through another component to be determined. Okay, and feed that into the tip of the amplifier this way. If we call I2 the current going through the device here, we have that I1 is equal to I2 is equal to I. Let's now see, and also we call the output V2. So we have that V2 is equal to KV, the voltage across the armatures of the operational amplifier. Let's see the principles of how this operational amplifier works by trying to put two resistors, R1 and R2, there. To understand the whole system, we need to write the different voltage equations we have here. And one of them is that, so V, the voltage across the armature here, must be equal to V2 plus the voltage across R2. So it will be V2 plus R2 I2. Now, of course, V2 is equal to KV as well. Okay? Or V equals V2 over K. Now, across this armature here, what we get is that V1 is equal to V plus R I1, which is I2. Okay, so let me erase this useless subscript 2 here and just call Ri with a 1 here. So we can rewrite this as V2 over K minus V2 is equal to R2 times I. Or in other terms, I is equal to V2 over R2 times 1 over K minus 1. Plugging this into here, we obtain that V1 is equal to V, but V is equal to V2 over K, plus R1 times over R2, times V2 times 1 over K minus 1. Or we obtain that V1 is equal to V2 times 1 over K plus R1 over R2 times 1 over K minus 1. Now when K is large, then we can write that V1 is approximately equal to V2 times, and that, by the way, this minus R1, this is not minus 1, my mistake, it is minus R1 over R2. Okay, so you get that V1 is equal to minus V2 times R1 over R2 with a minus sign in front of it. Okay, Now the good thing is that this is a pure relation which is independent of I, okay, and which we can rewrite as V2 is equal to minus R2 over R1 times V1, okay. What it does is it multiplies the input voltage by a particular output voltage in such a way. Multiplies the input voltage by a combination of resistance in order to obtain an output voltage like this. Okay. Now, let's look at other elements for the operational amplifier. Now that we have noticed that the number k here is huge, another way of saying it is that if V2 is finite, then V here is equal to 0, because V is equal to V2 over k. Okay, and we have constantly neglected V2 over k, so we call it 0. Okay, we can use this operational amplifier to do many other things. So, for example, let me clean up this whole area here. And this whole area there. In such a way that, and finally, erase our use of resistors. I first want to indicate to you that if I put R here and R there, we just get V2 is equal to minus V1. Therefore, we can use it to shift up or to switch the sign of voltages. Okay, so with two operational amplifiers, you can actually multiply a voltage by a positive gain. Now, let's erase this. And let's erase that. And let's put other elements here. So one of them could be, and will often be, a condensator. On the one hand, with a resistor on the other hand. Okay? In which case, what we obtain is that the voltage across the armature, okay, which is dV1 dt, and must be equal to I1 divided by C, okay, or C dV1 dt is equal to I1. Then we also have that V1, so that gives us I1. Now we have V2 plus RI2, okay, which is R times I, okay, because again I1 is equal to I2 is equal to I. V2 plus R times I must be equal to the voltage here, which is 0. Okay, so again I simplify my I's here and there. Now what do I get? I get that V2 plus R times C dV1 dt is equal to 0, or V2 is equal to minus RC dV1 dt. The output voltage is the derivative of the input voltage. Okay, so that's a pure derivative. Now, we can use this thing for other purposes. Okay, if you swap the role of the capacitor and that of the resistor, okay, so if we put a capacitor here of capacity C and a resistor here of resistance R, what do we obtain? Well, so the resistor R goes here, and the capacitor here, okay, with capacity C goes there. Now, what do we obtain? We obtain that RI1 is equal to V1. And again, this is R times I. Okay? With I1 equal to I2. Here is it here, here is it here, and here is it there. Okay? The other relationship that we have is that V2, that voltage, plus that voltage must be equal to 0. So V2 plus, what is that voltage? Well, that voltage is V, we'll call it V3, must be equal to 0, where dV3 dt is equal to 1 over C times I. So what we obtain is that dV3 dt is equal to 1 C times I, or in other terms, V1 over R. So we obtain that dV3 dt is equal to 1 over RC times V1. Okay. And this one tells us that dV2 dt is equal to dV3 dt minus dV3 dt, or in other terms, that minus dV2 dt plus dV2 dt is equal to minus 1 over RC times V1. Now, V2 is an integrator. Okay? It's an integrator. Okay, so we create these ideal components which are literally sort of logical components. Okay, and what we will do is we are going to use these components for the purpose of coming up with the appropriate logic that will help you establish control over mechanical systems. Now, one item which is becoming more and more important as time goes on is the electric motor. Indeed, an increasing number of operations on board aircraft are in fact governed by electric motors. So let's talk briefly about these electric motors. So an electric motor could be seen as the following. It's a machine, okay, that has a voltage at its input, okay, call it V, and that produces a torque at the output, okay, so torque tau, and that rotates at speed omega. So we have input voltage and intensity, output torque, and angular velocity. Now, the equation of a motor reads as follows. First, we have the equation about angular speed. So we call d dt. Oh, and by the way, this is for a brush motor. Okay, so a very classical brush motor. The angular speed is d dt of omega must be equal to 1 over I, the inertia of the motor, okay, times Ki of t minus B1 omega t minus F. What is this? Ki of t, it is just to say that the more there is an intensity, okay, the more the motor wants to turn, okay? So that's the input current. B1 corresponds, so it's like input power. That's losses, okay? Losses due to frictions. And that's external torque. The external torque applied to the motor, okay? So literally F should not be called F here, but instead tau. Okay? The second equation that drives the motor is about the intensity. d dt of intensity is equal to one over L times minus Ri of t minus Kb omega t plus V of t. This is the applied voltage. This is the resistive power, okay, and that's the back electromagnetic force, back EMF, okay. However, the important element is to notice that these are linear differential equations, and therefore they satisfy the conditions for which we can play with them using the Laplace transform. Let me add that L is the inductance. Okay. All right. So now what does that mean? That means that we have pretty much everything we need to design some logic and act on an electric system on a mechanical system via an electric system. Okay, we will see how to do that in the up-and-coming lectures. However, I wish and I hope that you can be patient, since this represents a rather advanced exercise. Thank you.